In this section of chapter 10, we will discuss about kinetic theory of gases, Graham's law of effusion, non-ideal behavior. Kinetic theory is based on a number of assumptions. Assumption number one tells us that gas molecules move at random and gas molecules have no dimension of their own, and basically they assume that gas molecules are like point particles like these, having occupy no space. And we know that this is oversimplification of real situation. Also, we assume that there is no attractive or repulsive forces between gas molecules. Again, this is also not right, especially as you lower the temperature or you have a higher pressure. When you bring gas molecules close together, attractive forces would be quite understandable because the gas molecules would then condense to liquid. But most of the temperatures, higher temperatures, it may appear that there is no attractive or repulsive forces between gas molecules. Average kinetic energy is proportional to temperature. When you increase temperature, average kinetic energy, which is given by half mass over velocity squared, is also going to increase when temperature is increased. Now here you're looking at molecular speed along x-axis and fraction of molecules along y-axis. Now, one thing that I'd like to point out to you is energy. First thing is energies are transferred between gas molecules during collisions. Even though that kind of transfer can happen, but the average kinetic energy still will be half mv squared. V is the velocity. That's an average kinetic energy. That only depends upon temperature and doesn't change with time, the average value. What that means is if half m u squared is a constant for a fixed temperature, if I have a lighter gas, that means if m is smaller, velocity has to be larger. So kinetic theory of gases correctly predicts that for lighter masses, velocity of gas molecules is larger. The gas molecules move faster when they're light. Again, here you're also looking at how temperature changes the average kinetic energy. Like here we are showing you two instances, one at 0 degrees centigrade, and for this particular gas molecule, less than half of the molecules move at speeds greater than 500 meters per second. On the other hand, when temperature is increased to 100 degrees centigrade, more than 50% of gas molecules move at a speed greater than 500 meters per second. So this tells us that average kinetic energy of gas molecules is proportional to temperature. Now we are going to explain what effusion is. If there is a tiny hole within the container of the gas molecule, then gas molecules would come out of that hole in such a way that lighter one would come out faster, heavier one would come out slower. In this figure, you're looking at a balloon filled with helium and the other balloon filled with argon. Let's assume that you made a tiny hole simultaneously on helium balloon as well as argon balloon. What you'd find that helium balloon is going to deflate faster than argon balloon. Now, can we understand that based on effusion? Answer is yes. Helium being lighter than argon, the gas from helium balloon comes out faster than the gas molecules from argon. In this slide, you're looking at Graham's law of effusion. Now, it's easy to derive it based on just kinetic energy expression. For fixed temperature, let's assume that temperature is fixed. So fixed temperature, average kinetic energy would be same for two gas molecules. Let's assume that gas molecule 1 has mass m1, velocity v1, and second gas compound or gas molecule would have mass m2 and velocity v2. So we set up an expression like this: half m1 v1 squared equal to half m2 v2 squared. Now then you do the math, and v2 by v1 equals to inverse of, you see that masses go in inverse order. Velocity 2, and it sees mass, that's inversely proportional to square root of mass of the gas that travels at speed v2. Now you can write down in a conventional unit v2. Instead of v2, we'd write down rate 2 over rate 1. So what you need to pay attention to is, for second gas molecule, its mass would be at the bottom. If you have rate of that gas molecule on the top, in mass expression it'd be on the bottom. So it's basically, I can write down that rate 1 is inversely proportional to the mass of component 1 or gas 1. So keep that in mind. Its rate depends inversely upon the masses, the square root of their masses. And we're going to apply this in solving problems. Let's now go over problem number 91 from chapter 10. So it's be 10.91. And this is coming from page 420, Brown Lemay Burston book, 12th edition. Now they're saying that arsenic 3 sulfide. Now they're all already telling you arsenic 3. So that means arsenic plus 3. And its sulfur is from oxygen group. It gets -2. So empirical formula, keep in mind, this gives empirical formula. So empirical formula for this formula will be given by As2 sulfur 3. So that's empirical formula. Now what they're saying is the molecules of the vapor phase are found to fuse through tiny hole at 0.28 times the rate of diffusion of argon atoms. So let's write down an expression. So what they're saying is the rate of this compound, arsenic compound, let's put down AsC, arsenic compound, we don't know the molecular formula yet, divide by rate of diffusion of argon equals to, methods would be now in this expression, but they'd be all inverse to the rates of those gases. So like arsenic sulfide, arsenic compound, when its rate is on the top, its mass would be in the bottom. So mass of arsenic compound, and on the top you'd have mass of argon. Now we know mass of argon from back of the book, and they also gave the ratio because they're telling you in this problem that the molecules, these molecules of this new compound, they come out 0.28 times faster than argon. So that means this value is 0.28. Let's write down 0.28 here. 0.28 equals to a square root of mass of argon. actually we can plug in the value of argon now. From periodic table we can find it to be 39.95. So let's use that number, 39.95, and on the bottom we have, let's write down the square root, the mass of arsenic compound. Now if you square it and solve it, then we are getting mass of arsenic compound equals to now in this particular case, of course, you'll have to first square it and then you get 0.078, and then you solve for m, and that gives you, let me write down the final step, 39.95. See whether you get the same thing or not. 0.078, and that gives 509.6. 509.6. So now we get the molecular weight in gram per mole for this new compound. We already know the empirical formula, so let's write down empirical formula is As2S3. So molecular formula is going to be a multiple of that. So we can write down molecular formula for arsenic compound equals to empirical formula As2S3 times N. That has to be multiplied by N. Here, N value is given by molecular weight divided by empirical formula weight. In earlier section you have learned this. So molecular weight is 510 and formula weight would be 2 times arsenic. So 2 times arsenic value is 74.92. That's the arsenic value. 2 times arsenic plus 3 times sulfur, plus 3 times the value of sulfur, which is 32.06. 32.06. Okay, let me remind you this. This is 2 times arsenic plus 3 times sulfur. Because we know empirical formula is As2S3. And now if you do the math, you're going to get 2.07. 2.07. And this number has to be an integral number. So we can round it off to 2 because it's so close to 2. What that means is molecular formula is 2 times empirical formula. So let me write down that. So molecular formula of this compound is As2S3 times N equals to 2. That's multiplicative factor. So we get As4S6. So that's our final answer. So make sure you understand that. Let me go over problem number 92. So that's 10.92. The question is, a gas of unknown molecular mass was allowed to fuse through a small opening under constant pressure conditions. It requires 105 seconds for 1 liter of the gas to fuse. So for the unknown gas, the rate 1 is for unknown, if you think it that way. So rate 1 equals to 1.0 liter divided by 105 second. So it's liter per second. So how fast this gas would be moving from one container through that hole to outside or another container. Okay, so that's given by 105 per second. And then R2 value similarly would be given by 1.0 liter divided by 31 second. This is for the second gas component, and they gave you this gas to be oxygen. So let's write down R2 is for O2, for oxygen. Okay, now let me show you for rate of diffusion based on Graham's law, rate 1 by rate 2 equals to a square root of M2 on the top, it's inversely proportionality, and M1 on the bottom, because R1 is on the top, so that's why M1 is on the bottom, and you have a square root of it. Now let's do some math here and make sure you plug in all these numbers. Rate 1 by rate 2, I think I can show you one more steps. Maybe 31, so from here we get 31 divided by 105. So 31 divided by 105 and that's equal to a square root of mass 2. Mass 2 is oxygen, so it's 32 divided by M1, and from here we get M1 equals to, let's write down here, 367 gram per mole. So let's read the question again, see whether we answered what they're asking for. So what they're saying is an unknown gas, it requires 105 seconds. I skipped first two lines. It requires 105 seconds for 1 liter of the gas to fuse. Under identical conditions, it requires 31 seconds for 1 liter of oxygen gas to fuse. Calculate the molar mass of the unknown gas. So molar mass for the unknown, we considered R1 to be unknown. So this one is unknown. So calculate the molar mass, and we already got the molar mass for the unknown gas. Here we're going to discuss about diffusion. Through this diffusion process, one gas compound or one gas component spreads into another gas compound, and that's why you get the mixture of these gases. And the speed, average speed of gas molecule will be given by this, square root of 3 RT over M. Again, it's the same R value, which is a constant, and T is the temperature in Kelvin, M is the molecular weight for that particular gas component. Here we're showing you real gases. In the real world, the behavior of gases conforms to the ideal gas equation at relatively high temperature and low pressure, when gas molecules are farther away from each other and they're highly energetic, so that whatever attraction they have, they're not really that visible. It doesn't make any visible effect. Now, it is also true that even the same gas will show quite different behavior under high pressure at different temperatures. So you're seeing it in this graph at different temperatures. You can see that as temperature is increased from 200 to 500 to 1000, the behavior is approaching the ideal gas, because ideal gas, you predict PV by RT for 1 mole of gas is going to be 1, and so that's the value is approaching 2 as temperature is increased. Now it is also, you can see here the difference between ideal gas and real gas. In ideal gas, there is no attractive forces among them. On the other hand, for real gas, you see on the right hand side, there is an attractive force within the gas molecules. And that would try to hold on to the gas molecules nearby. In other words, all the gas molecules cannot move freely. And so pressure would automatically go down, because pressure is due to collisions of these gas molecules on the surface of the container. Under high pressure, you bring gas molecules closer to each other. Then obviously their attractive forces be a lot more significant. Here we are showing you how ideal gas equation can be adjusted so that we can take into account all the deviations from the ideal behavior. Let me explain this to you with a simple diagram. Say I have a container with all these gas molecules. Now, okay, so now gas molecules. First, assume that they don't attract each other. And let's say my ideal pressure equals to 10. So I'm just making up this number, say 10 unit of pressure. That's for ideal gas. That means they don't attract each other. Now assume that they do attract each other. That means these molecules, which are approaching the surface of the container, would be attracted to other gas molecules. So would you expect actual pressure that you measure here is going to be 10? Our common sense would say it has to be less than 10, because some of these gas molecules are slowed down or stopped even by the other molecules because they attract. So that means they cannot freely go to the surface of the container and collide to exert pressure on the container. So let's assume that pressure that you measure here is 8. So basically what I'm saying is, in this bottom expression, 10 equals to 8. In order to set them equal, I must add a correction term. In our example, the correction term is 2. So we are doing the same thing in van der Waals expression. The modified version that I'm discussing here is given by van der Waals. Ideal pressure be given by measured pressure plus a correction term. In case of a volume, ideal volume is called free volume. Now, volume of the container would be free volume if gas molecules don't have their own volume. So they're like point masses. But in reality, they're not point masses. They have their own volume. That means, let me draw a little bit bigger molecule so that I can better explain to you. Since gas molecules have their own volume, that means other molecules cannot go through freely because of the presence of other molecules. They would go this way, it would collide and then go backward. So in other words, because of the presence of some of these gas molecules along the path, it cannot go freely. So in other words, total volume is not going to be the free volume. Think about a classroom when all the students are sitting. I, as an instructor, if I want to walk by, I cannot go to every part of the room because other students are sitting there. So my effective volume would be total volume of the room minus the correction term due to your presence and other students' presence in that classroom. Same is the case with gas molecules. Ideal volume would be given by total volume of the container minus the correction term, because of the fact gas molecules do have their own volume. Now that's what you see. This is measured pressure, and this is the correction factor for the pressure that's added. This is the volume of the container and subtracted, and that's a correction factor for the fact that gas molecules do occupy volume of their own, and that's equals to nRT. A and B values for different gases are given in this table, so you can plug in and get pressure, volume, temperature, whatever is needed in a particular calculation.